Welcome to another edition of Cosmic Nights. I'm Michael here at the H.R. McMillan Space Center. Thank you so much for joining us. If you have been to one of these online Cosmic Nights, we're getting pretty good with these once a month now, delving into themes. You kind of know how this works, but we've kind of did a bit of a different system here. So we've got some people in Zoom here, and we also have some people that are watching on YouTube, also on Telus Optics. So thank you so much to everyone that is tuning in out there. For those of you that are in Zoom, this is going to be a really special experience because we're going to hang out and we're going to have a really lively discussion around this topic of gas giants. This is a really cool one, and introduce our speakers a little bit later. But I'll first kind of go through some of the features of how this is going to work for everyone that is in Zoom. So if you're the first time in Zoom, you can kind of look around like the bottom there, and you can see that there's a couple different ways for you to interact with us. And I highly encourage you to use the chat feature. The chat feature is there for you to talk to each other. Maybe just say hi. And actually right now, if you could just put into the chat feature, where are you watching from? Let us know who you are. And so we'll say hi. And that's kind of there for just some banter. We've got some people in the background that'll banter back with you if you like. But if you want to ask questions, and this is kind of like our key thing of what we're doing here. Hey, Mark Wasson, if you're hanging out here in Zoom, is to use the Q&A feature. So you see on the bottom there, Q&A, that is where you want to put your questions. And the cool thing is that you can also upvote other people's questions. So if you see a question on there that you really want answered, say somebody asked, what is the meaning of life? And a bunch of people upvote it. You know what? We're going to answer that. And I'm not going to lie, I may say 42. And that's just from my perspective. I don't know what our guests would say about that. And the other cool thing is we got some polls. So our first little fun poll is, what's everyone drinking out there? It's 7 o'clock. Maybe you're drinking a beer. I've got my trusty soda stream here. But put on into the poll what everyone's drinking. Boy, I love that soda stream. It is one of the best modern inventions. I don't even drink regular water anymore. Put what you're drinking into the poll, and we'll do a couple more of these fun polls throughout the night. This is sort of like the real fun stuff that we get to do on online Cosmic Nights. So let's bring in some of our fun guests. It's not going to just be me talking about Jupiter and Saturn, the two gas giants. Of course, as always, we have our trusted astronomer, Rachel. How's it going, Rachel? Come on in here.
It's going well, thanks.
So how are you feeling about the gas giants? Which one's your favorite? Let's just go there.
Oh, I was hoping you wouldn't ask me that because it's really hard to choose between the two. But I might have to go with Saturn just because of its ears. I really like the rings, but they are quite close up there for my two favorite planets.
Awesome. So yeah, it looks like everyone's drinking water. It's a nice Wednesday night. It is quite hot, although it was raining here in Vancouver. So we'll see about that. Let's see who else we got here in the chat. We also got Lisa watching from Kitsilano. We got Debbie from Richmond. We got Parker here in Kits. We got Justin from the QE Park area. So welcome to all of you. So Rachel, a little bit later on, is going to be giving us like a very short presentation, which is going to lay out kind of the family tree of the solar system. So you know what a gas giant is, but you also need to know what the other planets are, because there are some distinct qualities to some of the other planets. So Rachel's going to lay that out in a really cool presentation. And a little bit later on, we're going to have a super awesome presentation. So happy to have Dr. Shawn Brooks, who is currently the Europa Clipper UVS investigative scientist and the Juno representative working out of the Jet Propulsion Laboratory, JPL. Isn't that super exciting? Rachel and I have been nerding out about how much we love JPL. They do awesome work there down there in Pasadena, California. So let's bring in Dr. Shawn Brooks and see what the weather is going on in Pasadena. See if we can bring hey,
Hi.
Dr. Brooks, how are you?
I'm all right. Good to be with you all tonight.
How are things down there in Pasadena?
Things are quite calm. It's going to be a pleasant evening, I think. Looking forward to a fun evening of science with y'all.
Yeah. It looks like you got a beautiful backdrop. I give you a 10 out of 10 on the room rater with you.
My little house.
Awesome. So let's start our conversation off with the two of you. Our first sort of like icebreaker question around this topic of gas giants. So we're going to get into Jupiter and Saturn. And Dr. Brooks, you have worked on the Cassini mission. I went to Saturn. Now the Juno mission going to Jupiter, and the next sort of big mission is for you, and also I think for NASA as well, is going to be going to Europa. So the real fun way to think about this is if you had the authority to choose where to go next. Oh, and of course, I forgot about Titan as well. So we're going to Titan as well. So you can't choose Titan or Europa. Where would you go next in the solar system? Let's start with you, Dr. Brooks.
Yeah, that's a pretty hard one. I mean, my heart would go towards Uranus or Neptune, and I'm not really sure which one I'd go with. It seems obvious to me to do something like that. It just sort of follows in the footsteps and the legacy of Voyager to go on to the next large planet in the system.
Yeah.
So maybe going to Neptune is kind of cheating and skipping Uranus. So maybe I'll just go with Uranus. We go to Uranus.
Well, I certainly, 8-year-old Michael is certainly happy with that because my last name is Unger. And I kind of had this like affinity with like the letter U. So I was like, oh, Uranus is my favorite planet because we share the same letter. That's kind of the thinking that 8-year-olds have. What about you, Rachel? Where would you go if you had the choice?
I would like to go to Enceladus. And I know that Cassini went by and sniffed the plumes of Enceladus, but I think that'd be really cool to go back there because Enceladus, much like Titan, were listed under the same kind of potential designation. That was these ocean worlds. And I think it might be cool to maybe compare like an ice core sample from Enceladus to something like an ice core sample from Lake Vostok, which is a subglacial lake in Antarctica. So that might be kind of cool to like compare and contrast.
Yeah, and that's really interesting. And maybe, Dr. Brooks, you could maybe chime in here. So if we were to go to Enceladus, would the mission kind of be very, and of course, the Europa Clipper mission is just an orbiter, but say if we were to like go on a lander mission to try to get under that ice, would it be very similar? Is like the makeup of Enceladus and Europa very similar?
There are some grossly, there are some similarities, right? Icy satellites with a known ocean beneath them. But there are a lot of things that make the environments very different. In some ways, if you were to do a lander on Enceladus, even though it's further from the sun, it might be easier. And one of the more challenging things we're going to face with putting a lander on Europa is the radiation environment. It's pretty harsh because it's sitting in the middle of Jupiter's magnetosphere. Jupiter has the most intense magnetosphere in the solar system, which I'll talk about later. And the radiation is so harsh that it really puts a short lifetime on anything that you want to land on the surface, that you want to expose. In fact, that's why the Europa Clipper mission will not orbit Europa, but it will orbit Jupiter and just dip in past Europa every now and again.
Okay.
So Enceladus would be in some ways easier to land on because you don't have to worry about radiation as much. You can sit there and look around for a lot longer.
Awesome. So the fun thing is that we asked some of our audience members to share with us. Our interactive activity was actually about that. Once we eventually get to that mission, once we land on Europa and can go underneath the surface and potentially, we're hoping, find some life down there, what would that life look like? So we got a couple submissions. Let's have a look at a few of those here. Here's our first one. If I can share the screen here, that's not the right one. And here we go. The land of labradorite. What do you think, Dr. Brooks? Is this looking pretty accurate to what you think we might find down here?
Accurate. I don't know about accurate, but there are no eyes, which I like. That would have eyes.
Yeah, of course. Yeah. So this is from Abby, 10 years old, and of course, yeah. Why would you need eyes if there's no light? And then of course, Mom Rebecca also has one here, and I'm just going to switch on over to hers. Oh, we do see an eye here, so maybe the eye is like seeing in a different wavelength, perhaps.
Well, yeah, we have these creatures, in the deep ocean of the Earth that. There's not much light there, but they have eyes because they actually have bioluminescence. So,
okay.
It's not that crazy. Very original. I like this.
All right. So, and of course, let's see what we got in the chat for where people want to go next. Pluto. Yeah. Like, what do you think about going back to, we were just there, but that was like a really quick encounter that we had with Pluto. But landing on Pluto was probably be like a pretty difficult endeavor because it got up there pretty quick, but slowing down seems like the biggest challenge with landing on Pluto, right?
Yeah, it really would be. I mean, it's just that it takes a big rocket to get yourself all the way out there and then slow down. I actually would probably sooner put an orbiter around Pluto than go land. New Horizons showed us so many things that we did not expect to see. I mean, Pluto looked nothing like what we thought, and so I think there's so much more to go back and investigate. Not just that the moon or the planet itself looked weird. It's just that it had all these different provinces or all these different areas where you could go to that looked nothing like each other.
Yeah.
So I'd want to orbit that guy.
Yeah, absolutely. Because there is also, I think there is a certain percentage of the planet that wasn't mapped out from New Horizons, right?
Yeah.
So there's still a bunch of mystery still left to unsolve. And I forgot to put up the poll. So I'm going to put up the poll here so people can where should we go next? I'm going to launch this poll so people here can chime in on where they want to go next. So we're going to take a quick little break here. Get your drinks all set up. We're going to watch a quick little video about Cassini to kind of get us hyped up about our gas giants. And then Rachel's going to come in with her presentation. Early votes are for Enceladus. Big votes for Enceladus. Go back there. So Dr. Brooks, if you have any influence, that's where the people are looking like they want to go here back to Enceladus. So we're gonna take a quick little break here and watch the video of the last images from the Cassini mission, and then Rachel's gonna come with her presentation. Don't go away. Just still gives me chills just watching that. Saturn, certainly one of my favorite planets. So let's go to you, Rachel, and for our first presentation of the night, the family tree of our solar system.
Thank you. So I'm going to share my screen here. So unlike our astronomer Q&As every Thursday, you will see actually the planetarium software that we use in the Star Theater. So you'll recognize that classic fisheye shape here, and you should be able to see the solar system. All right. So in our solar system, astronomers often divide the planets into two families, the inner rocky terrestrial planets and the outer giant planets. But what was responsible for this great divide, or family feud, if you will? Well, to answer this, we'll have to look at how our solar system first formed 4.5 billion years ago, and how it evolved over time to produce the order and arrangement of the planets that we see today. Now, the widely accepted theory of planet formation was jointly proposed by a geologist and astronomer. So the building blocks of planets, which we call planetesimals, were little bits of orbiting material that condensed into clumps, getting larger and larger until they grew big enough for gravity to shape them into spheres. Planets and moons were built up this way, and with comets and asteroids being the leftover debris. Now, around 2 decades ago, chemists realized that these planetesimals had very different compositions depending on their distance from the sun. Nearest to our star, only rocky material could withstand the heat of a young solar system. Thus, the first 4 planets are all small with solid rocky surfaces. Now, the planetesimals that form the outer Jovian planets contained higher concentrations of heavier and more volatile substances, which are referred to as ices. Now, this material settled in the outer regions of the early solar system, and it's here where gravity clamped this material together and formed the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune. But where do we draw the line for calling something a planet? Can I say that any large and roughly spherical chunk of rock is a planet? Well, exoplanet Pluto is a great example to explain the theory behind planet designations. So Pluto was once considered a planet up until new discoveries triggered scientific debate on how best to describe it. Now, the International Astronomical Union, or IAU, which is the recognized authority for assigning these designations and names to celestial bodies, like defining the 88 modern constellations. And in 2006, they came up with a definition for a planet. And they said that a planet must do 3 things. Number 1, that it must orbit a star in our cosmic neighborhood, that's the sun. The second is that it must be big enough to have enough gravity to force it and shape it into a sphere. And in physics terms, we call this condition hydrostatic equilibrium. And finally, the third is that it must be big enough that its gravity has cleared the neighborhood of its orbit. Now, unfortunately, Pluto fails the last condition, so it got demoted. In all of its billion years of existence, Pluto still hasn't cleaned up its home orbit, much like the state of my own home. Now, it too shares an orbital neighborhood with trans-Neptunian objects, things like Plutinos. Now, after our solar system formed, Jupiter took most of the material left over after the formation of the sun, and it ended up with around 2.5 times the combined mass of all the other bodies in the solar system. Now, gas giants are actually sometimes called failed stars because they contain the same basic elements of a star, and that's hydrogen and helium. Now, the term gas giant was coined in 1952 by a science fiction writer, and it originally referred to all the giant planets. But now we differentiate between gas and ice giants. So it's somewhat of a misnomer because the interior pressure is so high that matter is often not in this gaseous form. So as we descend further and further into Jupiter, we may see matter in something called a supercritical state, meaning that there isn't this defining line between liquids and gases. Now, if you've had decaf coffee, there is a non-zero chance you've encountered a supercritical process because sometimes people use carbon dioxide in this supercritical state to decaffeinate things like your coffee. Now, the bigger a planet becomes, the heavier the material is weighing down on its center. Now, at the core, the tremendous pressure causes temperatures in the centers of Jupiter and Saturn to be much hotter than the surface of the sun. And you go deep in their atmospheres, there's hydrogen gas that's compressed into a liquid. And this awards Jupiter the crown of the largest ocean in the solar system, an ocean made of hydrogen instead of water. Now, even deeper still, the pressure becomes so great that scientists think electrons can actually be squeezed off of hydrogen atoms, making the liquid electrically conducting, just like a metal would be. Now, of course, I can't talk about Jupiter without talking about its great red spot. Now, with no solid ground to weaken storms like we have here on Earth, this giant storm has run rampant on the planet's surface for many, many years. But astronomers have known for some time that the Great Red Spot is actually shrinking in size. And if it keeps shrinking at its current rate, it'll soon become circular by around 2040. And then we might have to change the name into the Great Red Circle. Although it is worth mentioning that even though it is shrinking in size, it won't ever be perfectly circular. And that's because there's strong opposing jet streams that define the spot's northern and southern boundaries, and those will always add a little bit of distortion to that circular shape. Now, like its fellow gas giant, Saturn is also a massive ball of mostly hydrogen and helium. It's also the only planet in our solar system whose average density is less than that of water. So if we could build a bathtub big enough to hold Saturn, it would actually float. Now, as a gas giant, Saturn doesn't have a true surface. The planet is mostly swirling gases and liquids deeper down, and at its center, it's a dense core of metals, things like iron and nickel. It looks a lot like Jupiter's core, but much smaller. Now, while a spacecraft wouldn't have anywhere to land, it wouldn't be able to fly through Saturn in one piece either. The extreme interior pressures and temperatures would melt and vaporize the spacecraft like it did in Cassini's final moments. Now, an interesting feature of Saturn is right at its north pole. It has a 6-sided jet stream. Now, this hexagonal pattern was first noticed in the images from Voyager 1 and more closely observed later by Cassini. Now, it's around 30,000 kilometers across with 320 kilometer per hour winds driving this massive rotating storm. And what's interesting is that similar shapes were created in laboratories here on Earth using a circular tank of liquid that was rotated at different speeds at its center and edges. Now, the most common shape found in laboratories was 6-sided, but shapes with 3 and 8 sides were also seen. Now, Saturn also has the greatest number of moons in our solar system, with a total of 82 moons, surpassing Jupiter, which has 79. Though Jupiter was the previous record holder, the discovery of 20 new moons announced by the IAU's Minor Planet Center last fall brought Saturn to be the champion of moons in our solar system. And we have 2 missions dedicated to studying 2 of Saturn's moons. We have Titan and Europa, and the latter of which Dr. Shawn Brooks is a part of, and we'll tell you a little bit more about later. And that brings me to the end of the solar system family tree, if you will. And Michael, I'll throw it back to you. Hopefully I've stopped sharing my screen.
Awesome. Thanks so much,
Great.
Rachel. So this is really interesting. You brought up, Uranus and Neptune in there. And of course, when I was going to school and we talked about the gas giants, we also talked about Uranus and Neptune, a part of the being in that family of gas giants. So what really brought about, did there a change to this? Do we no longer call Uranus and Neptune gas giants?
Yeah, so they're more commonly referred to as ice giants, and that's because this idea that they have this material that's called ices, and it's really referring to these volatile materials. And when I say volatile, I mean that it's material that likes to spend most of its time in a vapor-like state. And that's what we see here on Uranus and Neptune. So we've kind of gradually migrated from that gas giants term to encompass all 4 of the outer giant planets to moving into that separation and distinction between gas and ice giants.
Awesome. So in doing this, does this help us? Does this help astronomers, learn more about planets? Because it's all about names. Sometimes people get a little bit uppity when it comes to names, certainly when Pluto got demoted. So what is this all about? Like coming up with these different designations and changing things?
I think it is really important that we did make that shift from gas to ice giant. And we saw that with Pluto shifting from planet to dwarf planet. And even though I was a little bit hurt when they changed it, because like you, I also grew up with Pluto being a planet, it does help astronomers categorize it in our heads that, we're really just grouping this chunk of rock under a different name. And that name is dwarf planets, and they all share these similar characteristics as defined by the IAU. But I do think it is important to let go of some of those emotional feelings attached to names that we might have from just growing up to shifting to something that is more informative.
Awesome. Jump on in, go for it.
I'm going to add on, I think another reason that these distinctions come in is that it all gets back to understanding how the solar system formed, understanding that the timing of when Jupiter and Saturn formed, the fact that they are both so relatively enriched in hydrogen and helium has to do with their timing. They formed earlier, and being where they are, Uranus and Neptune also formed early. They do have hydrogen and helium, but not quite as early as Jupiter and Saturn. They were a little bit later to the game, which is why they aren't as big as Jupiter and Saturn. And then as those 4 large planets were forming and clearing out the area and throwing things around, a lot of things got thrown outward, and we now see a lot of those objects. And the other thing about this, another reason that Pluto got demoted, I think, basically, is that we now realize it's just one of many. And if we decided to keep it a planet, you'd basically have to choose between 8 planets or 1,000.
Right.
People often have a hard time remembering just the 9 names of the traditional planets. Imagine if you had to remember 1,000.
Yeah.
So,
the acronym, my very eager mother just served us 9 noodles or 9 pizzas, sorry, or served us noodles or 9 pizzas. I mean, it was just very complicated. You have like a really nonsensical sentence that you'd have to remember all the time. Let's get to some questions. And of course, anyone here in Zoom wants to jump on into the Q&A on Rachel's presentation. First one, which you already kind of answered, Dr. Brooks, which was by Justin. You wanted to know about the shrinking great spot. Why is it shrinking? And you said the classic science answer, which we all get excited about, which is we don't know. Is that
No.
basics?
Yeah, we just don't know. I mean, it's learning, watching it, will teach us about what's going on. But we are learning a lot about the Great Red Spot, and it's a big focus of interest on Juno.
Yeah, interesting. So, and if we jump on that question with Parker's question, which is about the hexagon, which may be related in some way, perhaps. Why is there a hexagon at the pole of Saturn instead of a circular spot?
I could jump on this one. So that's actually a question that I had as well, because you'd think that something that's so large, it's kind of weird that it would form a polygon, let alone something with 6 sides. And I believe the answer they found was when they ran these experiments in the laboratories trying to replicate that hexagonal storm, they found that it was actually this gradient or latitudinal gradient in differences in wind speeds and pressures that formed or happened to form this 6-sided shape. But of course, like I said, in laboratories, they were able to produce these shapes with different sides as well, 3 and 8 sides. So, it really is just a crazy phenomenon that's happening there out in space.
Dr. Brooks, is it aliens? It's not aliens.
Alien planet. Another way to think about it, the way that I get my head around it, is that it's really just think of a 6-lobe sinusoidal wave. And then imagine wrapping that around the pole of a planet. Well, that's what you'd get. You kind of get out a hexagon. So that's kind of the way that I get my head around this weird hexagonal shape. It falls out naturally when you think about it like that.
Yeah. Another question we'll go to Lisa, which is kind of a preview for our next Cosmic Night, which is all about exoplanets. So Lisa's heard about some exoplanets or exosystems that have gas giants located close to the star, more like our inner planets. Is our solar system unusual because of that?
Right now, I would say that is the $64,000 question when it comes to hunting for exoplanets. It turns out, are we unusual? Science went through, and maybe it's continually going through this evolution where we are trying to step away from being the center of the universe. That's 2,000 years ago, that's where we put the Earth, at the very center of the universe, and we have learned that we are not as exceptional as we think. It really would be weird if for some reason we just lived in this very unique solar system. And so you want to think that there are a lot more like ours. It would fit better. But the problem is that when you look for these exoplanetary systems, the ones with the big gas giants that are right near the star, those are the easiest ones to find. So the easiest ones to find are the ones that don't look like ours. So as we get better at it, we may find that in fact there are many more systems like ours, but we're just not quite there yet. It's pushing the technology, and it's a pretty exciting time to be an exoplanet scientist.
Rachel, what do you think?
Well, I actually had a follow-up question. So I'm wondering if in our search for exoplanets, we're right now focused on finding exoplanets that look a lot like Earth, because that's where we know life exists, and life as we know it only here in the universe. So I'm wondering if there are these other systems that could be more common, and when we're looking for exoplanets, looking for something that's close to Earth, are we missing out on any other potential worlds by looking at something that's close to Earth or similar to Earth?
I think it's something that people need to be thinking about as they do that. I think that's exactly right, because we know one type of life, but we really do need to keep an open mind if that's what the name of the game is.
All right, so I think what we're going to do here, we're going to take another quick break because we do want to get to your presentation, Dr. Brooks. So we're going to watch a really cool video. It's actually a brand new video that was processed with some citizen scientists, and this is a really cool new thing that is done on the Juno mission, which is there's a camera on Juno, but it wasn't there for science purposes. It was kind of there for citizen scientists to get in on some of these beautiful pictures and process them, because pretty much every picture that we see from space, it has to be processed. So for your bonus interview, for everyone that's here in Zoom, you'll get to hear an interview I did with Kevin Gill, who is one of those citizen scientists. He actually does work at JPL as a software engineer, but in his spare time, he processes some of these images. I had a really cool conversation with him. And you know what? The other day, I'm going to share with you this picture. After I interviewed Kevin, I walked into the Space Center, and if you've been to the Space Center, you may recognize this as sort of like the entryway into our gallery space. And I was kind of walking by, like, oh, there's a cool picture of Jupiter there. And there in the credits, you can sort of see there's an image credit there. And I saw Kevin Gill had processed this image that is this big picture that we have at the front of our gallery space. So, and also this little video that we're about to watch for our second break has some images also processed by Kevin Gill. Super cool. So make sure to check that out. And for everyone out there watching on if you go to the survey that was sent out, at the bottom of the survey, you'll get the link to that bonus interview as well. So let's take our second quick break and watch this really cool video from the Juno mission. All right. So as you probably saw, that wasn't all the Juno mission. There was a little bit of some extrapolation there, some animation. So the first image you saw was the image taken by Juno Cam that's orbiting Jupiter. And then they went into the animation to highlight some new discoveries that they have recently made. These things called mush balls. You sort of see these storms that are kind of brewing in this very turbulent atmosphere on Jupiter. And I don't know, Dr. Brooks, if you want to chime in and let us know. We're kind of talking about these mush balls that I've seen people talking about online. They're these really weird phenomena that certainly look cool if we were able to dive into the atmosphere of Jupiter like we saw in the animation.
So these are still, it's a theoretical construct, I would say right now. And where it's coming from is that Juno scientists are trying to understand the amounts of ammonia that they're seeing and the depths to which they see these large amounts of ammonia.
Yeah.
And so thinking about basically running thought experiments about what things must be like that deep in the cloud, beneath the clouds of Jupiter, that's sort of what they've kind of cooked up, that perhaps you can get ammonia up this high if you put it into these so-called mush balls that get lofted up higher up into the atmosphere. And eventually I think they would, I don't know if they would just evaporate or dissolve into the background, but that's sort of the idea, is how you get this enrichment. It's an attempt to explain the enrichment in ammonia that we see with the microwave radiometer on Juno.
Yeah. And of course, as always, the more things that Juno sees, the more mysteries just sort of keep to come up, you know, especially with like what's going on with the ammonia here. But let's get into your presentation, Dr. Brooks, digging into sort of like why we would or why we do explore Jupiter and Saturn in the first place.
Yeah, I think we have touched upon quite a number of the things I'd like to touch upon. Of course, I have put too many slides into my presentation, so I will try to make sure that I get it in on time and we have time for other questions. I see there are a few left in the Q&A.
Yeah.
So with that, I will go ahead and share my presentation.
Go for it.
All right, oops. And optimize screen share for video clip.
Yeah, I can see your screen. but you're also muted. I'm going to try to unmute you. For some reason, it's not allowing me to unmute you. Are you able to unmute yourself, Dr. Brooks? Oh, there you go.
I'm muted.
Yeah.
It didn't like something when I tried to share. My apologies. We tend to use different software when we do this conferencing at JPL, so sharing over Zoom is a little bit different. I'm going to try one more thing. If it happens again, let's see. Can you see my?
Yeah, I can see your screen.
Can you hear my voice?
Can you hear your voice? Yeah.
Okay, great. So I will go ahead and get into it.
Awesome.
So yes, exploring the gas giants. Let's talk about why it's such a big deal. So as we sort of touched upon, the gas giants are giants because they are so large. I did a sort of a back of the envelope calculation. If you were to add up the mass of Jupiter and Saturn, it's 80% of all the stuff in the solar system that isn't the sun. There's a little bit of a fudge factor in there because we don't know exactly how many of these Plutino and trans-Neptunian objects there are, and Rachel referred to those earlier. But I think conservatively speaking, they're at least 80% of what is out there. So as such, they are big and they are massive, and they have an outsized influence on the history and the formation of our solar system. So they're the focus of interest for, and as I note, space agency dollars, that definitely equates to something here for a multitude of reasons. They were key in driving the formation, the evolution of the solar system, as the graphic up here in the upper left shows. They are mini solar systems of their own. I've got an image here, a mosaic of the large moons of Jupiter, Io, Europa, Ganymede, and Callisto, and of course there are many more. So they're complex systems of their own that merit study. We talked a bit already about exoplanets, and I've got here an image of the Kepler 90 system, and the outer couple of planets are basically the size of our own gas giants in our own solar system. And the name of the game today is astrobiology. And so here are a couple of vents at a seafloor, and people like to imagine maybe that's what's going on at the seafloor of Europa, or perhaps Enceladus. And of course, it always comes back to the Earth. We see processes and phenomena that we can relate back to our own Earth. So we talked a little bit about Jupiter's magnetic fields, the aurora. Earth has similar systems, but they're different. And by studying these systems that are slightly different, we learn more about our own system. So I'm going to talk about our motivations for studying these two planets through the lens of two missions. We have Cassini, and there's a graphic of the Cassini orbiter on the left, and Juno on the right, which is currently at Jupiter. Juno launched from Florida back in August 2011, and it arrived on July 4th, 2016. I have to remember that. I didn't put that on the slide. Cassini left, of course, 15 years earlier. Pardon the background noise. And it arrived on July 1st, 2004. I remember that moment. It was a pretty big deal at JPL. We got there, and I recall seeing the signal come back from the spacecraft, letting us know that we had successfully fired our rockets and entered orbit at Saturn. As it so happened, when Juno got to Jupiter, I was not at JPL. I was in Italy, and it was 4 or 5 o'clock in the morning. Both spacecraft took a long time to get there, as I just mentioned, 5 years for Juno, 7 years for Cassini, because they kind of had to do these long looping paths through the solar system to get out to their respective targets. It is expensive, and we save our money. Instead of these direct launches like we can do with Mars, we tend to save our money on the mission itself as opposed to just getting it there quickly, which is unfortunate, but that's just sort of the way it is. We had infinite resources. Of course, we try to get there more quickly than we did. So first, I want to talk a little bit about Juno. It is a solar-powered mission at Jupiter, which first seems kind of a crazy idea, but we can do it. When the mission was built, trying to get the radioisotope generators that we use was a bit problematic. We didn't really have the material, and the PI knew that it'd probably be, if we could do it as a solar powered mission, that probably would fly quicker. So it's got 8 instruments and an outreach camera called Juno Cam that we've already talked about. That's got a great story to it too, and I'll come back to it. It is a spinning mission. So as you see these 3 big wings, they are constantly just, we are orbiting, we're spinning about that point where it says gravity science. That's, we radio all of our data back to Earth through that, and that's the axis about which we are constantly spinning. Juno is essentially we call it particles and fields mission at its core, because Juno is really looking primarily to study, or one of the big points of study is understanding Jupiter's magnetic field, and that's just best done on a spinning spacecraft. And as you can imagine, it makes it a little bit of a challenge to take pictures, but we have figured that out. So there are 4 basic themes of study for Jupiter. We have the origin of the solar system, not just Jupiter. We want to understand the interior of the planet. We want to map out the variations in the atmosphere and understand that a little bit better. And we already talked a little bit about the magnetosphere. So all these investigations look to answer some number of questions involved with these 4 categories. So I mentioned the formation, and basically one of the important aspects behind determining how Jupiter influenced the formation of the solar system is understanding how much water there is, basically, and how enriched these various atomic and molecular species are relative to the sun. And one of the things that we've already found out is that there is a lot of lightning. We've observed a lot of lightning, and it is much easier to make lightning out of a water cloud, or that as compared to the ammonia and ammonium clouds. I'm trying to remember what the other big cloud decks are. But because we see lightning, that implies there's a lot of water, and that also has implications on where Jupiter formed, how it formed, and what the supply of planetesimals to it must have been like. We've looked at the atmosphere, and we've discovered, and I'll come back to this, that it looks nothing like Saturn. On the left, we have 2 images from the Jovian Infrared Auroral Mapper, which is an Italian instrument, and it looks in the infrared. And we see these central cyclones at the pole, with these other cyclones sort of whirling around it. And I think there are 8 up north and just 5 in the south, and why, we don't know. We also have an image from Juno Cam on the right. Everyone recognizes the great red spot, which, as we mentioned, is shrinking. It'll be curious to see if that happens, if it stops, if it reverses. But I also point out Clyde's spot. This was discovered by an Australian amateur who was observing Jupiter and found this spot, and we've imaged it with Juno Cam. But what's cool about this is that it highlights the extent to which the amateur community is interacting with Juno. Not only do they process Juno Cam images, but amateurs with their own telescopes on the ground are constantly monitoring it and telling the Juno scientists, hey, new cool stuff, go check it out. The magnetic fields has been interesting and a surprise. Juno flies very close to the cloud tops of Jupiter. So close, actually, they asked me back when I had first got to JPL, and no one really knew who I was in the Juno project. Juno has rings. How close can we fly? And when I heard how close they were flying, I thought that could be a problem. Turns out we've managed it well, but we come within 5,000 or so kilometers of the cloud tops, which allows us to take measurements of Jupiter's magnetic field from really close up. And it turns out that from really close up, it's not the simple dipole field that we tend to think of. Of course, I would point out that that is exactly the same situation on Earth. The Earth has generally got a dipole magnetic field, but then there are anomalies as you get closer to it. So understanding how Jupiter could have these large variations from a dipole field is a subject of ongoing study, and it'll be interesting to see what it reveals about not just the magnetic field and the magnetosphere, but the interior of Jupiter as well. So this sort of gets at not just the magnetosphere, but it also gets at the interior of Jupiter. But wait, right, there is more. Not only do we look at the atmosphere, not only do we think about the origin and the interior, we can also look at the moons. And here's another image from that GIRM instrument, the Italian infrared mapper. And this is an image of Io. And basically every bright spot that you see is either a volcano or some hot spot on the surface of Io. Io is, for those who don't know, the most volcanic body in our solar system. We also recently got a series of images of Ganymede with GIRM, and we've just begun looking at those. There's a paper that will be due out soon. And we even use the navigational camera to get images of the rings. And so here's a picture of Jupiter's main ring. And for the sharp-eyed among you, you can even see Orion in the background, the 3 stars there, the belt towards the bottom of that image, and just up and left of center is Betelgeuse. Moving on to Cassini-Huygens, here's an image of the spacecraft before it left Earth, with the attached Huygens probe that was was launched towards Titan early on in the mission. I meant to actually put some slides, some images of the landing, but I didn't get around to that. That's okay, because don't have a lot of time. It's basically the size of a school bus. And as you can see, it's got a lot of complicated, a suite of instruments on it. There were 12, I believe, that we used. So when we got to Saturn, we really only were supposed to go for 4 years. Eventually, as you can see here, we got out, we were supposed to get there in 2004 and end the mission in 2008, but we actually wound up going all the way to 2017, ending the mission on September 15th, 2017. Like I said, these systems, they're not just planets, but they're whole mini solar systems in themselves. And this diagram shows you the planet itself, the rings, the large number of satellites that are worlds worthy of study on their own right. And then there's Titan, which is its own thing with its own atmosphere. It's the only moon in the solar system with an atmosphere. And this is what we saw of Titan when we flew by Voyager, kind of not terribly inspiring orange blob. That's what we could do. But Cassini was able to look beneath these clouds and found a lot of exciting things. We see clouds of methane up here at the upper left. We also managed to determine if there were lakes of liquid methane, and you can see the sun glinting off these lakes in the images on the bottom. And with the radar instrument, we could actually measure the size of these lakes. This one up here, Kraken Mare, I believe, is about 50% larger than Lake Superior and about as deep. Then there was Enceladus. We talked about the plumes. Here are images of the plumes, and it's also connected to the rings. There's this interconnectivity that should really be remembered here. We actually had hints that maybe Enceladus was related to the E-ring because that's where the peak brightness is of the E-ring, as you can see. And we did talk about the hexagon. Here's a movie of it. And this is the hexagon as it appears with a composite of data from the visual camera and the visible and infrared mapping spectrometer. And if you go into the very center, you see this hurricane. So remember how different that is from Jupiter. We have storms like this on the Earth, but not at the pole. And whereas Jupiter had this whole system of multiple cyclones, we just have this one great big hurricane, these huge eye walls at the northern pole of Saturn. And I want to talk briefly about this mystery of the rings, and I just lay out this map. For those of you who don't know it, we have the A ring, the very outer edge. The B ring is separated from the A ring by the Cassini division, and interior to that we have the C ring, and inside the D ring. And of course there are more. There's the F ring, which you can also see here, and the E ring that I talked about earlier. And one of the big things that we wanted to investigate was how old are the rings? So there's a little bit of a story here that I want to make sure that I get right while not taking up too much time. The rings are sitting here exposed to infalling stuff, micrometeorites, interplanetary dust particles. And they're collecting this stuff that is non-icy. So the rings are made of ice, and certain parts of the ring have more massive and certain parts are less massive. So the idea is that we could, if we knew the mass of the rings and we knew the infall rate of stuff, we could talk about how long they were exposed to the infalling micrometeorites and such. Let me explain a little further with something that is probably much more familiar to people who live up in Canada than people who live in Southern California. I grew up in New York, so I know all about this. Looking at this, you can tell where it snowed more recently. You've got infalling pollution if you live in a city, and the snow just tends to gather this stuff up. And this is the mental image that I like to keep in mind. The only difference with the rings is that it's as though someone were constantly stirring it up. So if you had a snowbank that was 1 foot thick and things were constantly falling on it, and you kept mixing it up, even though you mixed it up, eventually you would see all the pollution. Whereas if it were 10 feet thick and you kept mixing it up, it would take a lot more time. So we need to know how much stuff is there, and we need the infall rate of the pollution to use the pollution rate fraction that we see to infer an age. And at the very end, we were able to use Cassini to measure the mass of the rings, and we found it to be 0.6 times the mass of Saturn's moon, Mimas, which doesn't really mean a whole lot, the number in and of itself, but it implies that the rings are young, that they're not primordial. They weren't formed with the planet, which means that the Saturn that the dinosaurs knew, quote unquote, may have had no rings, which is a really intriguing idea, but it's not universally accepted. It's kind of a radical thought here. There's no obvious formation mechanisms for the rings in this scenario. I mean, you could have had some crash, some comet crash into a nearby moon, but that seems kind of unlikely. And you would think there'd be other evidence in the system, and we have yet to find it. And there's this whole idea of the exposure age that I just talked about versus the actual age. And there may be something in conflict there too, but it's something, it was a very exciting result that we got from Cassini. And I also, just having been involved with Cassini for the entire time that it was at Saturn, it was a pretty emotional thing to say goodbye to Cassini. I was there for the grand finale. I was there at the Von Karman Auditorium. My graduate school advisor is in the picture on the bottom right. And, you know, yeah, there were some genuine tears when we got the last radio signal. I want to share quickly a cartoon that we were shown. Someone mulling about what it must be like for Cassini to barrel into Saturn at the very end of its lifetime. Saturn not so sure about this idea. Awesome. So and here's my final slide. I just want to point out that I've talked about these two missions, but of course, these weren't the only probes to go to Jupiter and Saturn. We had Voyager, which those two probes explored the whole outer solar system. We had Galileo with its poor, not fully unfurled antenna. And we have future missions to come. The Europeans are launching their own mission to the Jupiter system, which should arrive at about the same time that the NASA mission to explore Europa will arrive. And we also recently had approved a mission to go to Titan, to have basically a drone fly through the atmosphere of Titan, and that'll be called Dragonfly. So there's been a lot of great things to study, and I am excited that there's a lot more that we will be able to study in the future, and a lot more great data that we're going to be getting back. So with that, I will end. Thank you for listening. I appreciate it.
Yeah, awesome. Thank you so much, Dr. Brooks. As the sun is going down on you out there in Pasadena, but it's great because we can still hear you. And you really touched on a few things there. And Rachel and I are going to grill you. And of course, everyone here in Zoom, get in on the Q&A for some questions for Dr. Brooks. But one thing, just emotionally, that really struck me, the Cassini mission was really a long mission, and you say that you worked on it from the beginning right there until the end. Is that model for a mission, is that going to be normal? Is that like super long missions, and like for someone like you to work on it for such a long period of time? And you must have changed a lot from the beginning, even just like personally from the beginning of the mission to the end of the mission. Could you maybe talk us a bit sort of about, I guess, missions in general being kind of like that length, and like maybe personally some of the growth that you did?
Well, I mean, yeah, I started working with Cassini and didn't have a girlfriend or any kids, and now I'm married with 2 children. But it's funny that you say from the beginning to the end, because I think that it's there's sort of this little chip on people's shoulder. Well, okay, you were there, when we got to Saturn, but I was there at launch. No, I was there when we first proposed it. So the kind of comes as like one-upsmanship.
Right.
Really, were you there the entire time? I think there's an interesting thing. I think that the scientists tend to stick around more, right?
Yeah.
So I'm working with Clipper now. We're still building it. And that was kind of exciting to me to get involved in the ground floor, probably for the reason that I just alluded to. But I plan to be there until we get to Europa, and that may not happen until 2030. Whereas I think the engineers tend to build it, and then they tend to move on to the next thing. So it's a little bit of both.
Interesting. Rachel, I know that you've been scouring some of Dr. Brooks' papers, and you've got some questions.
Yeah, I was reading a little bit on the white paper that was published outlining salient questions having to do with the Jupiter system and Saturn system. And I had a few questions. Yeah. One of my questions was, I read that by studying wave patterns in Saturn's rings, that researchers at UC Santa Cruz were able to extrapolate the spin period or the rotation period of Saturn. And I was wondering if you could speak to a little bit of how they did that and where these vibrations that were causing these wave patterns in the rings were coming from.
Yeah, I think that's some really cool stuff. It's referred to as chronoseismology. If you want to look up papers, look up chronoseismology. We have known for a long time that satellites exterior to the rings will raise these little like ripples in the rings. They cause these waves that you can see, and once you have a theory of how they form, you can back out a lot of properties of the ring. So they're of a great interest to ring scientists. But then we started finding ones where we couldn't find a satellite, and it turns out what was happening is that it was Saturn itself was raising these waves. So variations within the planet are being expressed in the rings. And one of the things that I tried to get across in that white paper was that we need to study rings because rings were cool, but because they can tell us something not just about themselves, but about the planets that they are circling. So by looking for these bending waves, these bending and density waves, we can actually learn something about the interior of the planet that we can't directly see. It's another way of studying the interiors.
Oh, interesting. Because you would think that ring systems and the associated planet are almost separate systems and separate entities, but it's interesting that you were able to figure out stuff about the interior structure from something external.
Yeah.
And just to maybe keep talking about rings for a second, you did talk, Dr. Brooks, about Jupiter having rings. And I just want to follow up on something that you had said. Did you say that the Juno mission people came to you because they were worried that their spacecraft was going to perhaps interact with these rings? Did you say that?
Yes. They knew that the mission architecture had been going inside the main ring of Jupiter, between the main ring and the planet.
Right.
There's an extension inward called the halo, but we don't really know much about it. One of the main differences between Jupiter's rings and Saturn's rings is they're so much more diaphanous. They're much more tenuous. There's just not much stuff there. But engineers will worry about the smallest particle hitting their camera or any other part of the spacecraft, so they have to quantify that in some way. And they convinced themselves that it wouldn't be a problem, and I think Juno has shown that it hasn't been. But there's been a very interesting paper that was recently published by one of the Juno teams looking at impacts on the spacecraft, and they do see them. They're small, and it I don't quite know what to make of it yet, but it looks like there is material inward, and it's too small to hurt the spacecraft, but there's some interesting dynamics that are going on there.
So it would you say that you wouldn't are you a bit worried that perhaps Juno may have an unexpected encounter, or you think it's pretty safe?
I think it's pretty safe. I mean, there's sort of the level of worry that an engineer will have, and then there's a level of worry that a scientist will have.
Right. Let's jump into just some of the questions that we got. And of course, this is a big question from Mark. Was there anything surprising that we learned from Cassini going around Saturn? Of course, I think the the answer to that is yes. So I think the real question is, what are the most surprising things that Cassini found around Saturn?
So I think he said when we flew into Saturn.
Oh yeah, I guess you can answer that question as well. So when we flew into the planet as well.
Yeah, I think that we are still kind of looking at some of that data and trying to understand it. I mean, there were so many things to talk about, though, just in general. I think the final 22 orbits of the mission were really exciting. Wait, I'm sorry, the final 42. I want to include the F ring and the proximal orbits. And there was so much that we'll be looking at this for decades. I wrote a grant proposal where I basically said, you have to realize that this will be the premier data set on an outer planet system for decades to come. There's a lot to unearth, and I only scratched the surface with some of the Cassini results. I mean, you can go on and on and on with that.
So future grad students will be delving into this for years to come. Is that what you're saying?
I'm certain of it. I'm certain there'll be theses written about Cassini data 20 years from now.
Yeah, well, that's the inspiration for anyone out there that's looking to finish their schooling. You could be just focus all on Cassini data. Another question here from Anonymous. Fantastic presentation, Dr. Brooks. In recent events, we've seen mission team members suited up in PPE in clean rooms, asking if that's the right term, while completing the Mars Perseverance rover. Have you worked within similar environments for the Juno, Cassini, or even the potentially Europa Clipper mission? What's it like in there?
I have not. I have gone to the clean room to go check out a mock-up of the Juno wings, which was pretty cool. But I'm not the one who's building it, so I haven't been doing that. And with the pandemic, JPL is really only allowing those of us who are physically building things to be there. So I know that there were Mars 2020 people who were there, and Europa is not quite at that stage. Actually, ironically, the instrument with which I'm working on Europa Clipper, they're looking at developing, they're looking at delivering our testing model that the project will use. And so they were talking about trying to get in there in September to deliver that model to JPL. And I thought, wait, I'm not going to be able to get to JPL by September. These people are going to get to JPL before I ever get to go back.
Right. They certainly seem really cool. I've always wanted to go into a clean room. It seems so safe now too. I need just to be in there and just be like, yeah, I'm in a clean room. I'm safe. There's no pandemic going to get me in here. Parker asks. Obviously, so the Europa Clipper mission is just going to orbit around Europa, but a submergible rover, is that a possibility? How long do you think until we can actually get something into the oceans of Europa and maybe even Enceladus?
Yeah, I mean, I don't want to be a buzzkill. I think that is a little ways off. I think that that would be a huge technological challenge. I think it would be difficult to do it on the Earth. But people are certainly thinking about it. One of our colleagues on Clipper actually does something just like what we're talking about here on the Earth. She works with a team that has a robot, and they put it beneath Antarctic ice and maneuver it around, and they're making a lot of progress there. So I do think it's a little ways off, but people are definitely interested in making progress towards those goals.
Right. Yeah, no, I mean, I've always, sort of envisioned that and been talking about it. And so I guess one of those things with missions is that, it's just in the idea phase right now. And I guess it's a little frustrating to think that, we may, live our entire lives and we still won't see the mission come to fruition. Like sometimes these missions, like from concept to reality, take a long time.
They can take a really long time. Really people will point to the beginning of Cassini being in 1990.
Right.
And I think that is an interesting challenge to go to Uranus or Neptune, some of these missions, particularly out there, because it really does take the dedication of people, of scientists and engineers who know they won't see the end result. They will have retired because it just takes that long to get these missions funded, then built, then launched, and actually arrive. But it's part of the process, and I look forward to being involved as long as I'm able.
Yeah. Awesome. Well, we are almost pretty much almost out of time. We're 5 minutes over, but we're going to end off with one last question that's going to lead into our special Q&A, which is how do citizen scientists get access to the Juno data? Can everyday people watching here, can they get in on these images?
Absolutely. I believe it is Mission Juno is the website you can go to look at some of the JunoCam images, and some of the images are relatively easy to work with. If you really want to get your hands dirty, you can always go to NASA's planetary data system, but those data are made publicly accessible. Typically, the instrument teams will hold on to them for a certain period so they can validate it and kind of get their first crack at it, but they are mandated to release all of that data to the public after a certain period. I think it's either 6 months or a year for Juno. It was 1 year for Cassini, but that's all available out there.
Really interesting. And we're going to put, so in the chat here in Zoom, we're going to put a link to that interview that I did with Kevin Gill. And then, of course, in the survey for everyone watching on YouTube, fill out that survey. Let us know how you like these events and what you'd like to see next time. And Dr. Brooks, have you ever actually worked with anyone, like a citizen scientist, asking any questions about some of the images from JunoCam?
No, I have not myself. But it would be enjoyable, I'm sure.
Interesting. So yeah, that's so good. Check that out. Check that interview with Kevin Gill. Dr. Brooks, thank you so much for taking time out of your busy schedule as the sun is literally going down there in Pasadena. Thank you so much for joining us.
Well, thank you for having me. It was a really great experience. I enjoyed it.
Awesome. Rachel, I will see you tomorrow. We will be live on YouTube at 2 p.m. With the exact same topic. So if you're inspired, have more questions, please join us on YouTube at 2 p.m. We'll be there talking about gassy giants. And for everyone out there watching, whether on YouTube, whether on Telos Optic, thank you so much for supporting us. If you haven't donated to us already, we really appreciate it. Keeps our doors open, keeps Rachel and I still with the Space Center. And please tell your friends. We are going to have so many of these online events. We have been doing a few in-person events. We will have a workshop all about extremophiles coming up in next month. I forgot about the robot one. We're going to be all about the robots that are on Mars right now. If you want to do an in-person experience with your family, socially distanced, of course, and in small groups, it'll be a really fun experience. So check out our events on our website, spacecenter.ca. Rachel, great to see you. Everyone out there, see you next time.
Bye.